To understand the differences between TCP and UDP, let's use a postal service as an illustration. Let's take the example of a registered shipment of several documents. Each document is sent in its own envelope. The mail tracking number corresponds to the sequence number of the IP package. The postal service will use any truck and any route to send the mail to the recipient. As this is a registered shipment, the carrier will ask the recipient to sign for each document to confirm to the sender that it's arrived. If an envelope is lost, the sender doesn't receive the acknowledgement, and thanks to the tracking number, they know which document they need to resend. This is how TCP works. UDP services, meanwhile, can be compared to sending a simple letter. The post office does its best to deliver the mail, but that's the end of it. There's no guarantee of delivery, and the post office won't be responsible if the letter is lost. Applications that use TCP need to ensure data is transferred reliably between hosts. TCP works at the TCP IP battery transport layer, which matches the 4-layer OSI model. It provides access to the network layer, that is layer 3 of the OSI model. It's a connection-oriented protocol. It requires a connection so that data can be exchanged. It can detect errors thanks to the checks made using the checksum field of the IP package. The checksum is a kind of negative of the rest of the header. When it's added to the other bits, the result should be 0. It's also known as a fingerprint. It allows the receiver to check if the message has arrived in its entirety. TCP works in full duplex mode. These segments are numbered and sequenced so that the receiver can put them back in order and see if any data is missing. Each time a TCP segment is received, the recipient sends an acknowledgement to the sender to confirm that it's correct. That's why we say TCP is reliable. It can request the replay of a segment to recover any data that's lost, and it can provide mechanisms to control the flow. The TCP header provides a lot of information. Each field has a very specific function. The source port field contains the port number the packet is sent from. The destination port field is the port that will receive the packet. Sequence number and acknowledgement number are used for reliability and to avoid congestion. The length of the header is the size of all these fields put together. The reserved field is set aside in case someone figures out a use for it in the future. The flags field contains several binary flags, on-off or 1-0, such as sync and acknowledgement exchanges. The window size field is the number of bytes the receiver wants to receive without acknowledgement. And the checksum field is a number that the receiver can use to check if there are any errors. Now let's move on to the features of UDP. UDP, User Datagram Protocol, includes several features that allow low latency data transmission. It's a simple protocol that provides basic functions. Like TCP, it works at the TCP IP battery transport layer. It provides applications with access to the network layer, without overloading reliability mechanisms. It's a seamless protocol, which means that segments will be sent to the destination without any notification. It simply performs a small error check. It provides better service, but does not guarantee data delivery. Packages can therefore be misdirected, duplicated, or lost. It also doesn't recover lost packages. It relies on applications to make this recovery. And with its low overload, UDP is ideal for applications like NS or NTP. This is what a UDP header looks like. Applications that primarily use UDP are DNS, Domain Name System for looking up the IP addresses behind domain names, SNMP, Simple Network Management Protocol, used by network admins to troubleshoot devices, DHCP, Dynamic Host Control Protocol for assigning IP addresses to devices on the network, RIP for routing, TFTP, Trivial File Transfer Protocol, and many online games and video streaming platforms. UDP and TCP use internal software ports to enable multiple connections between different network devices. To differentiate the data from each application, they both have fields in their headers to identify applications by port number. FTP, File Transfer Protocol, uses port 21 by default. It's a service used to transfer files between systems. On port 22, we can find SSH, Secure Shell, which allows remote access to other network devices. SSH messages are encrypted. Unlike Telnet, which uses port 23, Telnet is SSH's predecessor and does not encrypt messages. HTTP, Hypertext Transfer Protocol, uses port 80. It's mainly used by web browsers. HTTPS, HTTP Secure, is on port 443. It combines HTTP with an encryption layer called TLS, Transport Layer Secure. DNS, Domain Name System, uses port 53. It's used to resolve or convert Internet names to IP addresses. TFTP, Trivial File Transfer Protocol, which is a connectionless service, is on port 69. Routers use it to transfer configuration files and iOS images. And finally, we have SNMP on port 161. It's a protocol that works on the application layer. It allows network admins to manage network performance and solve problems. The core of Nagios, which is used for network supervision, is based on the SNMP protocol.